So, this is the second half of the Lancaster double wheel for this week. Steffen Grunewalder from Lancaster is going to talk about compressed empirical measures.
Yep, thanks for the invitation. So this is something I'm working on now for quite a few years, and I think it's slowly getting together. So it's a bit sketchy in parts, but I think there's an interesting story.
Okay. I remember
Just a bit sketchy.
Just a bit sketchy.
This caused some problems a little while ago. It did eventually come back, but it's
Good.
it might just be worth knocking on the door of the IT.
It might be. Check. Actually, my laptop. Oh. So I guess screen is fine. No, I'm not sure actually.
Yeah.
Okay, in any case, so this is stable and back. Something I'm working on for quite a while. So it's a bit of a mix between, I guess, some very simple empirical process theory. So I think there's a few people here who know these things much better than me, and a bit of optimization. So essentially what I'm interested in is large-scale statistics, but combine it with empirical process theory. So also for these guys who were here like on Tuesday, this talk will be quite different. I don't have any fancy videos, no fluid dynamics, no simulations. I don't even touch data. So it's quite a different style of talk. That being said, I have a few fancy graphics. So that's my usual motivation slide for this one here. In the middle we have empirical process theory. Since there's all these things you guys know much better than me. You have your asymptotics, you have your UCLTs, your Klevenko-Cantelli things, you have your Talakoa inequalities and all your finite sample guarantees. You have all your applications in non-parametric statistics. You have the Wapnick thing with empirical risk minimization, all these things. And the thing I'm interested in is essentially this new bubble here, which is, can we combine these things with techniques to scale things up to large-scale problems? So that's the thing I'm kind of looking at and will mainly talk about. I think the empirical process part is really quite minor here. It's possibly 2 slides, just the outline. What I really care about is only the empirical measure. So just to get the setting straight, what I'm caring about is IID data, x1 to xn, from some unknown probability measure p. And I'm estimating this measure with the empirical measure. So there's a bit of notation here. This usual notation Pn of f, which means nothing else than integrating f with respect to the empirical measure. Or if you like, you can also write this here as a sum with evaluations at xi. So Pm has these delta peaks at xi. So you have these general results that this measure converges uniformly over function spaces to the true measure. Pn is a good approximation of p uniformly over Donsker classes, so function classes that are somehow constrained in complexity, say VC classes and things like that. And here you have a rate of convergence, which is n minus 1/2. So there's this small issue here with outer measure versus measure, which I don't really care too much about. For me, the key thing here is you have a rate of n minus 1/2 of convergence uniformly over our function space of the empirical measure to the true unknown measure. In large-scale settings, the usual problem obviously is the computation time. So for instance, just as a really toy example here, say we do regression with samples x1, y1, xn, yn, sample from some true unknown measure p, and we're interested in finding a regressor. So we're trying to minimize squared error between y and our regression function over some function space. And here I've put in a regularization term, say some Tikhonov regularization or something like that. Then you usually get like a quadratic or cubic cost, something in between. And that is a problem if you go for large scale settings. If you have millions of data points, this cubic term will kill you. So you can't really apply these methods to large scale data. So the thing I'm kind of interested in, is there a way to reduce Pn in a suitable way while still gaining essentially the n minus 1/2 guarantees here? Can I replace Pn with something that's computationally more efficient while still gaining good guarantees for the approximation of the true unknown measure p? So yeah, essentially, can we reduce the size of Pn while still approximating P with the same rate of convergence? So I'll phrase it slightly differently. What I'm looking at here is, given Pn, so I have points x1 to xn sample points, can I find a new set of samples, x tilde 1 to x tilde m, in my input space x, such that m is significantly smaller than n, and the difference between the empirical measure and my newly selected points is uniformly over f small. So that's essentially what I care about. I guess you can come up with all sorts of approximations for measures. For me, it's really essentially a selection of new points from my input space x that I kind of want to extract in a meaningful way and get guarantees of that. So the approach I'm taking is essentially to move to a convex problem in Hilbert or Banach spaces, depending on what function spaces you work with, and use results for approximations of convex sets or elements inside convex sets to reduce Pn. So generally, P will be here some probability measure, unknown probability measure. B will generally be a Banach space. Quite often I will specialize to Hilbert spaces, and later on also to spaces which have continuous point evaluators. That's quite useful to control the convex sets, but I'm getting there a bit later. So the basic trick is quite simple. Say we have an expectation operator corresponding to our unknown measure P, which we can take expectations of functions in our Banach space. So we have an expectation operator that takes a function in our Banach space, produces a real valued number. If this thing is bounded, then we know there's an element in our dual space that represents this expectation operator. So E of f can be written as this dual element applied to f. Yeah, so bounded element, continuous element lies in the dual space. And this will hold for all elements in my Banach space. Why is this useful? So this is useful because I move essentially from this expectation operator to an element in a Banach space. So I move to some vector space where I can use convex analysis and approximation results. And the main thing here is, next step here is very often there exists a convex set C as a subset of my Banach space in which this measure M will lie. So very often you can localize M within a convex set, and you can get control over this convex set to start approximating the measure. So I should possibly say, I think for large parts of the talk, I don't really assume that M corresponds directly to the empirical measure. So just in the end, I kind of will specialize to that. So the idea is pretty much as a sketch. This one here, I have, think of that as being the dual space, B star, so some element M here. I have a convex set that contains them, so we'll talk a bit later about how to gain these sets. And what I'm interested in is I try to approximate M with the sets of extremes of the convex set. So this is classical result from function analysis. If your convex set is compact, then Klein-Millman tells you you can describe any point inside your convex set as a limit of convex combinations of the extremes. Yep, sure.
So I don't understand what you say. So M is just one point. So a point in a vector space is always in a convex set.
Sure. I care here about particular convex sets that I have control over. So I'll talk about later. So essentially, what's happening here, to forward a bit, these things will correspond to point evaluators, and that will later on, so it's quite going a bit forward, but this will later on allow me to choose points here. So it's not, obviously, I mean, the Hilbert space itself is convex, or the Banach space itself is convex. I care about particular convex sets over which I have control.
Right, so the construction of the convex set we will have to speak about.
So the construction.
Okay, just carry on.
So the convex set's going to be determined by the selection of the points.
Exactly. So there's quite a natural choice for these convex sets, for the extremes. Yes, so yeah, in practice what I will do, I will not try to go from a convex set to the extremes, but I will describe the extremes, and I will know that M will lie in the closed convex hull spanned by these extremes.
And you're always thinking deterministically about selecting these points.
Oh yeah, there's nothing stochastic here. It's all deterministic. So I have a measure given, I have a represent a given offset measure in my function space. I have the convex set given, and I'm just running a convex approximation algorithm on these things. And I'm interested essentially in the rate of convergence of these algorithms, because that will tell me how many points do I need to represent the measure. So just a bit of an outline in the literature. Actually, someone pointed me to this one here, which I didn't know about, but this is a big topic in approximation theory. So there's like a book recently from Temnyakov, if I pronounce him correctly, but there's a lot of research, I think, in the last 15 years on so-called greedy approximations of functions in Hilbert and Banach spaces. If you have like a basis, like say a Schauder basis with a Banach space. So these are essentially selection algorithms where you in a greedy fashion try to select elements of your basis to approximate an element F. So I'm not an expert of this one here, but this is a quite typical approach. And this is in some way, I guess, related to what I'm doing. Just the main difference here is instead of working with a linear space and a basis, I'm now doing greedy algorithms. I'll explain in a second what exactly I mean by that. But essentially greedy approximation algorithms that use the extremes of the convex set to approximate M. Greedy is usually important in these things because you want to save computation time. So I want to reduce Pn to a small set to be later on able to run algorithms efficiently, but obviously if it costs me a lot of time to extract these points out of Pn, if this itself is a bottleneck, I will not gain anything. So I need fast algorithms that can get me a good approximation of my measures, and usually the best candidate for these things are greedy algorithms. So more graphics. So roughly the settings I care about. The gray area is the thing I'm kind of mainly concerned with. I need some property which is called uniformly convexity of my Banach space. I'll explain in a second what that is, for the approximation algorithms to work. So it's essentially saying something about how the norm ball bends. There must be some bending of the norm balls. To efficiently be able to run these algorithms at the moment, I need something, need essentially continuous point evaluators, which is essentially saying my Banach or Hilbert space should be continuously embedded in the continuous functions to be able to have bounded point evaluators. So I need this one here to run things efficiently. Essentially it's this egg or ellipse or whatever it is. And I need this ellipse if I want to gain guarantees. So this is kind of the intersection where things are nice. RKHS stands for reproducing Hilbert space. It's essentially a Hilbert space that can be continuously embedded in the continuous functions. For these things work nicely. So there's a bit obviously of spaces. Obviously there's spaces which don't have continuous point evaluators, say L2. L2 is Hilbert space, it's uniformly convex, but doesn't have continuous point evaluators. Similarly, there's points here, so you have actually spaces which have continuous point evaluation, but are not uniformly convex. So there's you rule out certain spaces here on both sides, and this is the kind of area I'm interested in. So the majority of results will be for Hilbert spaces and some extensions for Banach spaces. Just to give the definition, uniform convexity is essentially saying you take the unit sphere, take 2 points on the unit sphere, you go to the middle must lie deep inside the unit ball. So if you think of the unit sphere, take 2 arbitrary points, take the line in between. This guy here should lie far away from the norm ball. So formally, you can also write this obviously formally. So it's essentially saying you pick an epsilon, then there is a delta, such that if x and y are at least epsilon apart, so these guys shouldn't obviously lie at the same point, but need to be reasonably far apart, then the middle between x and y, so this point here, has radius 1 minus delta. So this here corresponds to norm 1, and this point here must have a norm relatively smaller than, so here quantified by delta. There's also ways to measure the convexity of the ball, but I don't need this at this point. So I think the main intuition that you need here is the ball needs to bend. You need to have something which lies inside if you take a line between these. So what this is ruling out is, for instance, L1 or L infinity, which are not uniformly convex, so you couldn't work with these. But for instance, every other LP space is uniformly convex. So how does the algorithm work? Essentially, you have a set of candidates from which you can pick. So I call this, I think, hopefully consistently throughout as capital S. So it's essentially my set of points I will work with. I need to make sure that the set of points contains the extremes of my convex set. So because otherwise there might be obviously points I can't represent. And what I'm interested in is the set C, which is spanned by S. And I call this here the closed convex hull of S. So CCH in the future stands for closed convex hull of my set of candidates from which I choose. So I need some topological properties here. I don't think this is not too important, but I need some form of compactness or by default optimization. In this case here, weakly compact is sufficient, so you can work with that. The methods are greedy. Another word to say that is they work iteratively and produce a sequence of elements S1 to ST. Later on, I'll show how you can relate these back to points in your sample space. But essentially, you get a sequence of elements, and the approximation itself is super simple. It takes a sequence of elements, you just sum them, so you get a convex combination of these by weighting them as 1 over t. So it's essentially giving you an element inside the convex hull. Simplest possible convex combination of the sequence you choose. So generally I use this MT to denote the approximations, or MN, I think I've changed in between the index a bit. So for the approximation, for the algorithms, they usually rely on an approximation error, which I denote here as WT. WT is essentially a scaled up version of the difference between M and the approximation. So it's essentially T times the approximation error, your current approximation error. So WT tracks essentially your approximation error. So you try essentially to keep WT small or even reduce it. So the algorithms, I have essentially 3 versions here. I hope it doesn't get too confusing. The outline is pretty much the same for all 3. They're also extremely simple. So you initialize W0 with your unknown measure M. So you must have here some control, obviously, over M, but you try to get a representation of M that is computationally, I guess, easier to handle. Then you iterate. It's an iterative algorithm. At each stage, you choose an element out of your candidates that minimizes the next approximation error. So if you choose it, you get the smallest approximation error at the next step. So this one here on the right side is essentially WT plus 1. WT plus 1 is the approximation error at T plus 1. And this is argmin. You're minimizing this approximation error at the next step. So you're choosing an element S such that your new approximation error is as small as possible at T plus 1. So the problem with that algorithm is the norm here makes some problems computationally. So this thing will still cost me something like n squared per iteration. So it's not really a big reduction yet of computation time. So this one here is still not kind of what I'm aiming for, but it's much easier to analyze and has better guarantees in terms of the approximation error. Yep.
You speak of reduction in computation, doesn't this crucially depend on how you choose the set C, I mean the convex set?
Yeah, obviously it will depend on the size. So later on, the set C, the set S.
I don't understand at all yet how you choose C in a concrete case.
So in a,
C depends on the unknown distribution P, so,
yeah.
So how do you choose it in this algorithm is not clear.
Okay, I mean, I can possibly step a bit forward, explain this one first. This is,
Well, I mean, it's fine if you explain
No,
later,
let me
but how do
quickly
you
go
speak
there.
of a reduction in computation time? You
Sure.
should explain
I
how
think
to
it's
choose.
possibly good if I go there quickly. Should possibly shuffle these things a bit around. So the idea is pretty much, I think, hopefully I'm now in the picture. The idea is pretty much, And here's pretty much this last line here. So if you have point evaluators, if you have continuous point evaluators, just forget all the rest at the moment. So it's just these two lines here I'm caring about. So if you have continuous point evaluators, which I denote here with Lx, Lx is my continuous point evaluator. If I integrate these with respect to P, so in this sense, because these are elements in my Banach space, this would be a Bochner integral. Since this thing here is the same as my representer M of the measure. So there's an integral representation of the element in the dual space. This M has an integral representation in terms of point evaluators. So you can write this as, essentially as this Bochner integral, Lx dp. So this here is the kind of key. Sorry, it's possibly a bit small. But you can represent this element in your dual space as a Bochner integral with respect to your measure P over your point evaluators. And this Bochner integral representation tells you that M lies in the closed convex hull spanned by your point evaluators. So you can treat the Bochner integral as an averaging process over the Lx elements. So M itself will lie in the closed convex hull of your point evaluators. And my candidates then, later on, are essentially these point evaluators. If I go over Lx, I will be sure that M lies in the closed convex hull spanned by these Lx.
You still have a uncountable number of point evaluators.
Sure. In practice, what you need to do is
discretize this whole computation cost will become an issue, and I don't know how you discretize it because the optimal discretization will probably depend on P.
Okay, so one thing with these greedy algorithms, you never go for optimal. So if I try to find the optimal representation of my measure, I will definitely have massive computational issues. In practice, what you will do here, and yeah, I agree there's an issue. Obviously, you ideally want to go over the whole set. In practice, what you do, and I think I'm not sure if my results work for this one yet fully, you will replace this one here with Lx1 to Lxn. So you will take essentially the convex set span. So if you work with the empirical measure, you use the convex set spanned by your point evaluators pinned down at your sample points. And then the computation times n. So you have essentially n samples. So you need to go at each step over these n samples only. So you have a natural, I guess, natural discretization here. Is that kind of, yeah?
And you use the word samples, but you're picking these deterministic.
So these ones here are now the true samples x1 to xn. So by convex set, so I have like some samples from my measure P, so I have x1 to xn, which are drawn from my unknown measure P. And essentially what I'm doing, I'm pinning down points in my P star space. I mean, that's how I would apply it for the empirical measure. And then I'm trying to approximate Mn. Essentially, this is convex set spanned by the points. Yep, so this makes it a bit more clear. Any other questions?
I mean, I still don't see obviously why when you do this is computationally more efficient than just computing the empirical measure. I mean, because you have to evaluate Pn of f for a fixed depth, so you have to, that also needs n steps.
So this one here, I think the algorithm, one of the algorithms I'm using is essentially using runtime n times square root n to produce a compressed version of the empirical measure. So significantly lower, and then you would have a version of the empirical measure which has only square root n many points. So you would reduce.
You don't take n points here.
No, this one you still have. So in each iteration, I need to loop over all n. In each iteration, I need n, and I need around square root n many iterations. So I have n to the power of 3/2 computation time to compress the measure. So yes, this is, I guess, the most expensive operations. In each iteration, I need to loop here over n elements. But I have not too many iterations. So you get something, this is one something down to n 3/2. And I think, so the algorithm I'm essentially here evaluating is the easiest possible. So there's algorithms where I think you can go down to n log n, and then have a compressed version of the empirical measure which should be of size log n. which definitely will give you a massive boost if you run anything like regression or anything else. Okay, so let me figure where I was before. Okay, algorithms, so I think I'll have to speed up a bit. So essentially, there's like 3 algorithms written here. First one, I minimize the approximation error in the next step greedily. So again, this will not give me the best possible choice of points S1 to Sn. It's a trade-off between getting something reasonable and not wasting too much time on optimization. The update of the approximation error after choosing a point is essentially the difference betwn S star and my unknown measure, which I add, and this will essentially give me my new approximation error. There's 2 alternatives. The alternative that is the most computationally efficient is this one here. So you replace this step where you go over the norm and instead look at the inner product between your current error and an element from your candidate set. So you try to essentially align the element of your candidate set as well as possible with the error term WT. So this one here is the algorithm which has n square root n computation done. So because this norm evaluation is expensive, this one here is essentially applying these point evaluators to the empirical measure. This has runtime n in each iteration, and then I need around square root n many iterations. So there's a third version, which is, I think, only for theoretical purposes useful. The big problem in this setting is you essentially will apply these things to compact sets, and some of the directions in which you want to minimize the error have only very small, I guess, span in your convex set. So n lies very tight to the boundary. So you have only a very small direction there. That is kind of leading to the main problems in this algorithm. So an alternative to kind of circumvent this in certain ways to rescale these directions, to normalize them. So if this thing is super small, I'll kind of normalize it and get a longer vector. So that's a version that's not really practically useful, but it's easier to analyze. So this one here, I would say, is the easiest one. This one here is also still easy to analyze, but this is essentially the one you kind of would like to have guarantees for. So yeah, so as a whole, I think time-wise, I'll probably skip that. So you can extend these things. So this is at the moment for Hilbert spaces. You have inner products here. You can obviously generalize this guy here directly to Banach spaces. But you could also think of, is there a version of this one here for Banach space, which would be quite interesting. So I have some slides on that, but I'll skip over that. So the only version for the Banach space I'll look at is essentially the same one we have just seen. I initialize my error term with the unknown measure, that I kind of for the measure that I want to compress, and that I greedily at each step minimize the norm. The measure and the approximation error now live all in the dual space, so I use here the star to denote that. But beyond that, the algorithm is exactly the same. So I'll skip through these things. So now the more interesting things, the rates of convergence for these algorithms. So here's a simple proposition. B star, I assume these things to be separable. As I said already, I need something, as I called it earlier, uniformly convex. B being uniformly convex is equivalent to B star being uniformly smooth. So these are dual notions, also essentially related to the bending of the norm ball. So that's crucial here. I'll explain hopefully in a second why. I have my convex set as an element of my subset of my dual space. Assumes this thing to be bounded, convex. And the main assumption here is I assume that it contains an open ball, which is centered around M. So I need in my set somewhere, say my set is here, I need an open ball around that set for these guarantees to work. So essentially what this is guaranteeing me is that I have in each direction, wherever the error wanders, I have in each direction at least some element which is aligned with it. So that is what this ball is guaranteeing. If If I wouldn't have that ball, there can be directions in which I can't really reduce the error. And that would essentially screw my runtime guarantees. And if I have this open ball around M, then I can guarantee for this one here an approximation error of mt minus n of a rate 1 on t. So there's some constant b, which I here don't really care about, but I have a compression of t minus 1. So it goes down linearly in t. I feel it's different.
So if I look at this example for C that you gave by these point evaluators, I mean, if you want this to have contain an open ball, you will need a countable set of points at least.
So yeah, I'm coming to that. So yeah, in practice this will not work. If
If you discretize this condition is not satisfied.
2-3 slides, we're coming to that, yes? So there's a problem with that, yes. So but for a start here, I think that's an important thing with the open ball. If this thing works, it kind of characterizes how the algorithm would run. I think we can skip here over this one. It's just a dual definition of uniform convexity. So how the algorithm works, as a small sketch here. Essentially what you want to show in these algorithms is that this term WT stays bounded. So if you recall, WT is essentially a scaled version of the approximation error. So it's essentially T times the approximation error. So if this thing here is smaller or equal b, then obviously m minus mt is smaller or equal e divided by t. So essentially what one cares about in this proof is to show that WT doesn't cross certain boundaries. Main intuition is the method essentially acts like a contraction if WT gets large. So inside it can kind of fluctuate around, you don't really know what's happening, but as soon as you cross a certain threshold, a certain horizon, the operator essentially, this update operator essentially acts like a contraction. And the argument is the following here, using exactly this kind of ball assumption. So you can first see that there's an element x star. So I've changed notation here slightly. X star is now an element of my candidate set centered at M. So there's an element x star because of this ball assumption, which is well aligned with the error. And if I subtract this x star, which is some x minus m element, I will get a reduction in norm. So this ball essentially guarantees me if WT, I think I might need a size assumption of WT, but it's essentially guaranteeing me for large WT that if I would choose this element from my convex set, then my error at the next step will be smaller. I will have a contraction factor, here 1 minus delta times my old norm. So this would guarantee me boundedness if I would choose this particular x star. Because if I'm going out too far, eventually this thing will guarantee me that my norm decreases. So difficulty here is you need to move from x star to candidates S from which I can only optimize them. X star is an element in this set, could be an arbitrary element, could be an element in my convex hull. So it's not directly accessible to me through my candidate set S. But what we obviously know is x star is a limit of convex combinations of elements in my candidates. Because any element in C I can represent as a limit of convex combinations of my extremes, and my extremes are a subset of the elements I'm optimizing over. So what's now happening is x star reduces this norm. Now I need to carry this one over to the convex combination. So I have this figure here down here. Let's say this one here is WT minus x star, and x star for simplicity is just a convex combination of 2 points, say S1 and S2. This one here would be W2 minus say S1. This one here would be W2 minus S2, and the convex combination gives me my x star. So what I need to know now is that at least one of these guys has a norm smaller than WT itself. So in this figure here, this is a ball of radius WT. This has norm WT times 1 minus delta. this point here, if I would choose this S, I would get a larger norm, so I wouldn't get a contraction. But this point here reduces the norm. What I need for this one, or why I need smoothness for this one, if you think of sorry, L1 norm, you would have a point here. So this guy is a convex combination of 2 points. So we'll go to the left and to the right. So it's such a convex combination. So both these points could have actually a larger norm than WT. So even though X star reduces my norm, these 2 points might still increase my norm. But what happens with this uniform smoothness is essentially my norm ball, as the ball size increases, gets flatter and flatter. If I take points here, these points must lie within that norm ball. And however I align them, there must be at least one point which lies in this WT normed ball. So one of these guys must at least reduce my error. And in my greedy algorithms, I select essentially the point from my candidate set which decreases the error most. So these guys here will be lower bounds on how much I reduce the error. I'm not sure if this is too fast, but essentially the idea is uniform smoothness guarantees me that the norm ball will look very flat if I go far out, if my ball size increases, and then I'm guaranteed that at least one of my guys who forms a convex combination of X star will reduce the error such that I lie inside the norm ball. So that's where this uniform smoothness comes in. So these things wouldn't work for L1 or L infinity, because here I couldn't guarantee, I would know there's a point which reduces my norm X star, but I wouldn't know that this carries over to the extremes which generate that point. Is that understandable? Any questions here for the outline, sketch? No, that's a bit fast, probably. Yeah, I can explain, if anyone is really curious, I can explain this a bit later in more detail. I think the intuition is not too tough. Given that I'm a bit running out of time, kind of just trying to stick, I guess, to the main story. So one of the problems, I guess it links to what Richard said. In practice, what you want is the convex set to be reasonably small. You don't want a massive set. You have optimization problems if I go over a really large set. So natural assumption here would be, for instance, that the set is compact or weakly compact. C shouldn't be too large in size. So for instance, say a simple thing is, you could say your sample space is a compact space, 0-1 interval, for instance, your samples live in the 0-1 interval, and you're interested in continuous functions which embeds this thing. So that's coming, I guess, from an RKHS background. But you would link essentially your sample points to candidates. Here I'm working now with a Hilbert space instead of a Banach space. You embed these to form the extremes of a convex set. What happens here is then, if you apply a continuous function to a compact space, you get again a compact space, and also the closed convex hull operation preserves compactness. So what you get is that the set C, which is the closed convex hull of phi of x, will also be compact. Is that obvious why this is a problem in infinite dimensions for this proof? So in this proof, the main assumption was this open ball assumption. If you have a compact set in an infinite dimensional function space, then there exists no open ball inside that compact set. Compact set collapses as you go along your basis. It needs to shrink to 0 as you go along. So actually this thing here, this proof here, will not work for compact sets. For this very natural setting, we have like a continuous map, compact input space where your samples live. This proof does not work because there is no open ball. There can't exist an open ball around your measure. And that is obviously quite a bummer, quite a problem, because that is the setting you really care about. Computation, you want to work with that. So I kind of tried quite a while to figure out ways around it. And also, I guess, first, is that a problem of the proof technique? So one could say, possibly I don't need an open ball around M, possibly there's a better proof technique, which still gives me my guarantees. Can I find something like that? So I guess there was a bit of this open problem. Is it a wrong proof technique, or do there actually exist compact sets where the convergence is slower than 1 on T? So I kind of constructed some example which was, I guess, a bit horrible in the end. So there's like a counterexample which is like, I think, 8-9 pages long. The main intuition is not too tough if anyone cares. I can possibly explain this later. But essentially, for this fast algorithm, so algorithm 2 was the one which uses the inner product, I used the nicest possible setting. So here, reproducing current Hilbert space. So it's a Hilbert space. It has a continuous point evaluator, so it's pretty much as nice as it gets. There's usually this notion here of continuity, how your point evaluators change as you change your input points. Here I use the continuous kernel function, so also this one is really nice. Use the input space 0, 1. I don't think there's anything wrong with this one here. And the measure P, I don't remember how regular P was, but I don't think it was like a particularly horrible measure. And for this setting, I could show that the algorithm leads to an approximation error W2 that diverges, which means I can't get this rate of 1 on T. So it has nothing to do with the proof technique. There is a real problem here with compact sets, which is essentially what I said, I think, earlier. This thing here, if I have certain directions where I just don't have any elements with which I can reduce the approximation error, then WT can wander off in that direction and can get large in that direction. So there's a bit of ideas on what to do with that, because obviously compact sets are the thing you're interested in. So you kind of start thinking about what are alternatives, how can I get around this problem. I guess one natural assumption would be, can I somehow restrict the size on C? So the counterexample I have is really massive, has a very slow decrease in terms of span as I go along the basis. So it's a very massive one. So you could think of, could I try something like some currying number constraints on my compact set and see if that is helpful. So I tried this for quite a bit, but I didn't really get anywhere with that one. Seems quite natural, but yeah, with this one here, I'm stuck. You could think of adding further assumptions beyond compactness. So if I manage, I will quickly talk about something there. I think there's possibilities here to replace the ball with something else, for which I can then guarantee rates of convergence, at least for some of the algorithms. Or the other one is, you might also think of moving to other forms of guarantees. At the moment I get guarantees in norm. I approximate my element in norm, which I guess are the strongest possible guarantees. So you could also think of weaker guarantees. So I'm just thinking what to go into and what not. I mean, about these weaker guarantees, essentially one thing you could think of, instead of having norm guarantees, you could look into something like that. You could say, instead of caring that I'm good with respect to the norm ball, I only want to be good with respect to the elements in my convex set, which are anyway the elements I can describe well, and I want to have a good approximation error just for these elements. So it's a weaker form, I guess, of measuring the error. Has also, I guess, a bit of natural appeal, that I essentially want to be good, have a good approximation error for these elements, or which I actually optimize. I'm anyway going over these guys, so I kind of want to be good over all of this convex set, but that I don't necessarily need to be good in directions that I don't optimize over, that I possibly don't care about. So it's a different form of convergence. For this one can quite easily get something, so there's a bit of a symmetry assumption which I don't want to talk about here, about the convex set. But essentially what you get here is you have your 1 on T rate of convergence. So here's the approximation error uniformly over my convex set. T here I moved to the left side, but essentially this is B over T, move this on the left side. Because the problem here is I get an ugly lim-inf here. So I know I will always decrease below a certain level B over T, but in between the approximation error can wander off. And I actually couldn't figure out how long these wandering off periods are. So it might get quite horrible in between. Eventually it will go down again to B over T, but then might wander off. So this is showing, okay, it's not like possibly too off, but this lim-inf really is kind of not very appealing. So the question was then for me, I guess, for quite a while, the main question, how can you get around that? How can you avoid system imps? There should be some natural assumption that works for compact sets and guarantees good compression, because that's really the setting you care about.
Can you just ask what is the conditional on P here? I mean, it's completely arbitrary.
So the expectation is with respect to P.
Yeah, so P is any arbitrary probability measure.
Could be, yeah. I don't think I need any. I don't think I need any restrictions. Let me think.
Does
Missing
the
something?
constant P depend on P or not?
Sorry?
Does the constant P depend on P?
I think the constant can be, yes. I should need to look it up. I could imagine. So it definitely depends on the convex set. I'm just thinking if it depends on how far this guy is, how close it is to the boundary, and these things in certain directions. I'm not 100% sure. I think it depends only on the diameter and size of these sets. I don't think it depends on P itself. I could look it up. I don't remember exactly. It definitely depends on the geometry of this thing. I don't think it depends on P itself. Okay, in any case, so this is kind of, I guess, halfway good, still not what one wants. So, I guess that slide looks a bit horrible, but I guess that's kind of the main idea now, how to get something better out of it. So this normal assumption doesn't work, but for the inner product, essentially what I looked into, if I have somewhere the point M here, I have an arbitrary direction X. I think I use F on the slides. I want to be sure that some point in my candidate set S lies within an angle of P quarter to that point. So essentially I have like a cone here, and in this cone there must be somewhere a point S in my candidate set, for whatever direction X I choose. So what this one is essentially saying, even so I might not be able to represent this direction exactly, which would be a normal assumption, which would be this assumption here, I should at least be able to have something that is reasonably aligned with that element. So I kind of weaken this normal assumption to saying, I let you get away with not being like super good here, but this would be something which is aligned with X. And that is something that can be fulfilled for compact sets in infinite dimensional spaces. And you can get guarantees for that. So I think, given time, I possibly would just state the result here. So the assumption I call this, okay, I dubbed it a P quarter dense, meaning for every X, I have an element which is within angle P quarter of that point. Doesn't matter too much. For this thing, what I can provide now, depending on which algorithm I choose, algorithm 1 was the algorithm where I optimized over the norm. Algorithm 3 was the algorithm where I optimized over the direction, but the direction is normalized. Both of these algorithms are unfortunately computationally not what I want. Algorithm 2 is really what I want. But for these things, at the moment at least, I can provide guarantees. So for these things, what I can show quite easily for algorithm 3, if I optimize essentially all my candidates, I kind of normalize this here. I know this error stays bounded over all time points. More importantly, algorithm 1 here guarantees me that my norm over WTs stays at all times bounded. So this one here is essentially telling me if I have a compact set that has this P-quarter denseness property and I use my first algorithm, then I'm guaranteed that I can compress the empirical measure down to square root n many points, effectively, something like that. So yeah, so that was something I think one can improve these things still quite a bit, but that was something I kind of was looking for quite a while, an alternative to an open ball, which weakens that assumptions, works with compact sets in infinite dimensions, and yeah, this is one assumption here that works. So I think this was all up to here just about optimization. So you can obviously also look into the interplay between the measure and your point evaluators, and also the measure and its position within the convex set. So usually here in these settings, what seems nice is if the measure lies deep within the convex set and not close to the boundary. And you can translate certain properties of P into the locations of M. So I have like a few slides here on that one, but I think I'll not go too deep into that one. The first one was the one we had a bit earlier. Essentially, it's this Bochner integral representation, which tells you M itself will lie within the convex set spanned by your point evaluators, but you can do more than that. You can say something more about how deep the thing lies in certain directions within that set. I think I'll skip over that if anyone's interested. I'm still around today. So I think just probably for the end, coming to the empirical measure, moving back to this one here. So you can write the empirical measure if you're on this Banach space setting as the point evaluators pinned down at my samples x1 to xn applied to f. So here I have just a function f in a Banach space B. Lxi is the point evaluator living in B star that essentially evaluates f at the point xi, and xi would here correspond, should possibly have used the capital X, corresponds to my sample. So I have essentially here a representation of my empirical measure in my dual space, such that this is equal over all of the, if I integrate with respect to the empirical measure. So there's now two things that can happen. Okay, sorry, notation confused me a second. I should have used here a different notation. So these are not the same xi's as this one here. Should have, sorry for that. Should have called this possibly yi. So there's two things that can happen. I can have either a sequence yi in my dual space such that the point evaluator over the sequence converges to M. So which would be essentially saying I can compress the empirical measure into a single point up to an epsilon approximation error. So that's something that would be obviously quite nice, but it's not really the realistic case. So this is one thing that can happen. The second thing that can happen, so either of these two will happen. The second thing that can happen is that this p-quarter denseness property carries eventually over, this is my approximation error from the UCLT is good enough, carries eventually over from M to my approximation Mn. So I have like a true, so say, since I was sitting here, I have somewhere a true M. Then I have my representation of my empirical measure, say Mn. These things will eventually get close due to the UCLT. And what I'm saying here is, eventually as this thing gets close to this one, this p-quarter denseness property, if it holds for M, will also hold for Mn. So there's obviously the property is a problem. I actually don't have good criterion for this one yet. There's obviously the problem of characterizing which convex sets, together with which measures, have this p-quarter denseness property. So that's a separate problem. All I'm saying here is, if it happens to be that M has this property, then Mn eventually will also have that property. So it will also be able to approximate, to use Mn and approximate this one well. Yeah, this is essentially not too tough. All I'm checking here is essentially if I can approximate well with certain directions. All I'm saying here is if I use the empirical measure, the difference between evaluating with respect to the empirical measures and evaluating with the true measure is bounded up to some constants, independent of the difference in norm between the representative of the empirical measure and the true measure. And this thing here, because of the UCLT, will eventually go to 0. So the angles I measure will essentially be at one point, I guess it makes intuitive sense, will at one point be the same angles that I measure with N, and this kind of p-quarter denseness property carries over. So I think I kind of, yeah, sorry for rushing through that. I think there was a lot of stuff I skipped over. Wasn't really sure with the timing, but just to give a few points here. So there's still a lot of open problems for me here in this thing. I mean, there's already a lot of stuff there, it took me a lot of effort, but there's a lot of open problems, just to mention a few. I think this p-quarter denseness is nice, but you kind of would hope for so that you can reduce this further, go to bigger angles, instead of just having this cone, could you kind of widen this one? Would also be interesting still to see if you can use some form of covering number constraint or something on your set C to enforce good convergence. So in the counterexamples, the size of the set definitely matters, and so one can wonder if the set is in a certain way small, does it allow me to guarantee fast convergence, which would be obviously very different from these geometric properties where I just need to be able to represent elements well. But yeah, so this one here, I couldn't really come up with anything, but it feels there should be something here in terms of coverings. Bigger problem, I guess, practical problem. The thing I just showed about p-quarter denseness works for the two algorithms which are unfortunately not the fastest. So the question is there a possibility to carry this over, for instance, for the inner product algorithm or a similar algorithm for Banach spaces? Okay, I think that's it. If there's any further questions.
I'm trying to figure out what's going on.
Oh, okay. Sorry for that. I mean, I crammed a lot. I should really apologize. I think I crammed a lot of stuff into a few slides.
But it would seem to me that knowledge about P would be critical to knowing how you're going to find some small subset to be able to use the measure there. So in some sense, your method is trying to learn about P, but it seems that what you're trying to do is to look at structure where you have sort of very close local approximations and you can move it. Is that right at all?
Let me see. So, I mean, first, I think the P itself definitely factors in significantly, and I don't have a really nice link between things yet, but I always try to figure out properties of P that translate to some geometric properties of varied license complex sets. So this one, I definitely agree. It's definitely important. Properties of P definitely matter. About the local thing, I don't fully understand.
Well, what it is I'm trying to figure out where is it that you are learning about P, because for this method to somehow work, it has to be,
I guess,
learning it.
so I guess the first one obviously is Pn itself, which contains a lot of information. So the samples x1 to xn contain obviously due to the UCLT a lot of information about P itself, and then I guess the step from Pn to the approximation. So where's this factoring in? I guess it comes back to the localization of
So it's just that if you're learning locally, are you learning globally?
okay, so this one again, I don't forget. So if I'm
I don't know.
I think what Ed is saying that is very important here is that basically in this point evaluation example, what you're saying is you're representing P as a convex, as a linear combination of certain sort of basis functions, which are your point evaluations.
Yeah.
So
So
basically you're doing some sort of non-parametric smoothing, and your results are kind of very general in P. Whereas really, if you want to get good bounds, what you'll have to say is that P somehow has a nice representation, sparse or decaying in these point evaluators, because basically you're just doing some sort of convex variation of non-parametric statistics ideas here. And so I think your results, like this whole question of whether you can take C sort of small, I imagine that this will be admissible if you assume that P somehow has a good representation in the basis functions that you're using, which you're using here, sort of point evaluators.
okay, so possibly one thing.
So I think the fact I think that somehow your theory suffers from the fact that you're not making any appropriate assumptions on P.
Could be. So one thing first. It's not linear. It's convex. So I'm not really using as a basis. So I guess coming back to the Temniakov stuff, that would be, I guess, the more natural analog where you have actually a vector space with your basis. So here it's not really a basis of the vector space. Quite a different representation.
No, but you're writing P as an integral of the point evaluators dP. So you clearly this is in the convex hull of the point evaluator.
Sure,
so
it is in the convex hull. Exactly.
Convex hull, so there's a linear procedure there.
Yeah. So I guess I definitely agree that P should possibly factor in stronger in the approximation guarantees. So I guess it's part I skipped over, which I'm always trying to link to, and I guess I just didn't get a good handle on how to link the properties of P to, I guess, through properties of the location in the convex hull to the approximation guarantee. So I agree, there should be some natural links there.
take your set C that is compact and small, and you
Yeah.
will have to sort of quantify the approximation error of the representation of P in the full open set of point evaluators by those that are constrained to line C. So it's just a standard bias very straight off.
I mean, okay, so M itself will automatically, as long as the Bochner integral exists, lie in the convex, closed convex
Yeah,
hull.
but you want
over
to quantify the approximation error, that if you restrict your convex hull to coming from fewer linear functionals, you will have to say how much you lose in reconstructing P.
Sure. So I'm kind of definitely, I have my convex hull itself, which will be the full ball, and I'll go only over a few points. So yes, you could also, I guess, if you treat it, say I take the 0-1 interval, have a map to the point evaluator as a continuous map, since the 0-1 interval essentially represents my whole convex set where I'm sure M lies in, and now I essentially discretize, I guess that's what you're saying. So I essentially discretize based on my points. So obviously then if my representation is very fast changing, so say I have this continuous map, if this has bad smoothness properties, I guess there could be something like that happening too, which I didn't think about. So I guess what you're saying really is this map into this space, if this can be very rough, I can have problems that my discretization will not represent my convex set well. I guess that's what you're saying roughly. Yes, there could be something like that. I didn't think about that, but yeah, you could potentially think about this map and smoothness properties of that map to say how good do these finite many points, this thing spanned, represent C. Yeah, I agree. Yep.
You started with the motivation that for the large scale problem I need this compression from P and F to some other measure that you are coming at the end like to M and F. But I'm wondering like whether you are actually gaining anything in like computing P and F and computing M and F, whether there is actually any.
You mean because no,
like but you are saying like you have a compression from Pn to Mn, but I'm just wondering whether that
So
final
you have P, you have like Pn, and then you have like the compression.
compression, yeah.
Squared n, yeah.
Yeah, but then the compression, the time is actually, when you are computing that compression, whether you are actually gaining anything in the
Okay,
terms
yeah.
of the.
I think that's what I said, I think a bit earlier. So the compression, if I'm actually able to work this algorithm too, the compression will take me n3½ runtime. I think this can go down to n log n, so you have this upfront runtime. But then you essentially work, instead of like the normal computational cost, you work with something like, say, log n to the power 3. Or
But then that the runtime that you're saying, like n power 3/2, that would probably depend on the size of C, right? For different C, you may have a.
okay, I mean, this will depend on, again, on the convergence guarantees. If I can converge, if I can guarantee here convergence of 1/t, I guess that's where C comes in. So then I will have a compression of down to.
I mean, what I
square
was
root.
trying to say, basically, your runtime would be some function of the size of the C.
So yeah, C will definitely factor in. I mean, that's essentially the things I'm trying here. If I have certain nice properties of C, I can guarantee a runtime. Yes, essentially. Okay, thanks.
Okay, just a reminder that this is the first instance of INI bribery this afternoon at 3:30. Sweets will be available. So please come out to the Metzing.
Okay, thanks.